Hi, 8th grade. For science today, we are going on to 4.13, and it's Newton's first and second laws of motion. If you think of Isaac Newton, you might think of the apple dropping and landing on his head. That's kind of the picture that you see of Isaac Newton when it comes to his laws of gravity and motion. So we're going to talk about him today. So we are on page 207 in your book. We're going to read through and then I'll go over what your lab looks like for today. So Newton's first and second laws of motion. Isaac Newton carefully observed how motion works on the universe and developed 3 laws to describe motion. One of these, Newton's first law of motion, is called the law of inertia. This law states that a body or an object at rest remains at rest unless acted on by an unbalanced force, and a body in motion continues to move in a constant velocity until acted on by an unbalanced force. Inertia is the tendency of an object to resist a change in its movement, regardless of whether it is in rest or in motion. If it is still, it remains still. If it is moving, it keeps moving in a straight line and at a constant speed. In one sense, all objects in the universe are lazy. Objects can change. The word inertia comes from the Latin word which means lazy. Objects change their fixed state only if a force acts on them. An object that is still does not randomly move. A book on a table will remain in that position until someone moves it. Moving an object speeds up, slows down, or changes direction only when a force, such as friction, acts on it. A bowling ball continues moving until something, the bowling pins or a gutter, stops it moving. So, for instance, in space, if you were to throw something into space, it would keep going for eternity, because we don't know how far the expanses of the universe are, but it would keep going because there is no force out in space where there's no gravitational pull. You have no friction slowing it down or speeding it up. So it's just going to keep moving. So once you send that off, the force at which it has to move forward, it's going to keep moving forward. If you were to send, let's say, a Matchbox car down a hill, it'll pick up speed and go faster and faster because of that gravitational pull pulling it down. But eventually, as that hill levels out, it'll slowly come to a stop because of the friction of the road on the tires, and there's no downward slope to give it that forward momentum, and it'll eventually stop. The inertia of an object is directly related to its mass. The more mass of an object, the more force is needed to get it moving with a certain acceleration. For example, compare how much force you need to move a pebble and how much force you would need to move a large boulder with the same acceleration. The pebble is not very massive, so it has little inertia, and it takes little force to move it. The boulder is massive, and it has more inertia and requires more force to move it. Newton's second law of motion applies here, which states that the net force applied to an object equals the object's mass multiplied by acceleration. It takes more force to produce the same acceleration in an object that have more mass. This law can be stated with the formula F equals m times a, sometimes rearranged to a equals F divided by m. In this formula, F is the net force acting on an object, m is the mass of the object, and a is the acceleration of the object. The metric units of mass are in kilograms, the units of acceleration are meters per second squared, and the units of force are newtons. 1 newton equals 1 kilogram times a meter per second squared. If a 60 kilogram object is pushed and it accelerates at 3 meters per second squared, the resulting net force, F, is 180 newtons. Net force is the sum of all forces on an object, so it includes the opposing forces in friction. Suppose the frictional force, F1, equals 580 newtons, and the force exerted is Fp. To find out how much force is actually exerted, use the following equation. Fp minus FF equals F. When you solve for Fp, you find that you actually have to apply 760 newtons of force to gain a net force of 180 newtons. So if you think of that in real life terms, if you were to push a pebble down a hill, you could just flick it. It wouldn't take much energy or much inertia because it doesn't have a lot of mass. So it's easy to push. Now, if you had a boulder right next to it and you wanted to push that down the hill, that's going to take a lot more initial force to get it moving, but it's going to move at a much faster rate and probably for longer as well because its mass is heavier than that pebble is going to roll down the hill. A biography of Sir Isaac Newton. Sir Isaac Newton was born in a small English village in 1643 and is regarded as one of the greatest intellect of the scientific revolution of the 17th century. His father, who was a farmer, died before Newton was born prematurely. His mother remarried when he was 3, leaving him in the care of his grandmother. Newton attended school until his mother, widowed a second time, took him from a school age of 12 to learn farming. He failed at farming and was sent back to school. Eventually, he entered Trinity College in Cambridge, where he worked on a campus, waiting tables and cleaning to pay for his education. Although much of Europe had embraced new scientific philosophies, such as heliocentrism, Cambridge had not. Newton was taught the traditional science curriculum in class, but read the modern philosophers and scientists in his spare time. He graduated without receiving any honors, just as the Great Plague forced Cambridge to close. For 18 months, Newton studied alone at home. Sounds like us right now. Hopefully not for 18 months, though. Newton studied alone at home. During that time, he developed infinitesimal calculus, beginning his theory of light and color, and pondering gravity and planetary motion. In 1667, he returned to Cambridge, where he earned his Master's of Arts and became a professor. In 1668, Newton invented the first reflecting telescope to help prove his theory of light and color. A bitter rivalry developed between Newton and Robert Hooke, the foremost authority on optics at the time. Unable to bear criticism, Newton withdrew from the society for 6 years. During this time, he formulated his laws of motion, which were published in Philosophiae Naturalis Principia Mathematica in 1687, a book that is still regarded as the single most influential work in physics. Isaac Newton was elected president of the Royal Society in 1703 and was knighted by Queen Anne in 1705. It's amazing what can be done in the life of a person. A boy whose father had died, his stepfather died. He was a terrible farmer. Looking at that, you would think, wow, he really does not have a good outlook on life based off of his beginnings. But he worked hard and he studied and he questioned the science that was currently being taught. And because of that, we have a lot of our understanding of the world around us today because he pushed forward and he asked the questions and he did the research, even with a background that was not maybe ideal. He pushed through and he made something of himself, and he also did wonderful things for the scientific community that we can understand today. Going on to the next page, gravity. Gravity is the force that causes an object to drop to accelerate towards the earth, or objects that are dropped to accelerate towards the earth. All objects near the earth's surface accelerate at a rate of 9.8 meters per second. This is called the acceleration of gravity. This means that for every second an object falls, its downward velocity increases by 9.8 meters per second squared. This acceleration is the same for all objects, regardless of their mass. If a 2-kilogram box falls on top of a shelf and lands on your foot, what would be the net force of the impact? F equals 2 kilograms times 9.8 meters per second squared. F would equal 19.6 newtons. That would hurt, but it probably would not cause any damage. What would be the net force of a 20-kilogram box if it fell on your foot? Your foot would receive a 196 newton of force. Even though the acceleration rate is the same for all objects, regardless of the mass, the force definitely changes. These examples did not take any frictional force into consideration, but frictional forces exist and must be considered. When a tennis ball is dropped from a very tall building, it is assumed that the velocity of the tennis ball will continuously increase as it accelerates. Actually, the tennis ball will not gain velocity quite as predicted because of a frictional force that is also pushing up on the ball. The force, known as air resistance, acts against the free fall of the ball. The net force acting on the ball is the force of gravity minus the force of air resistance. This resistance increases as the velocity of the ball increases until the point is reached where the upward force of air resistance equals the downward force of gravity. At this point, the object stops accelerating and starts falling at a constant velocity. The constant velocity at which an object stops accelerating is called its terminal velocity. Terminal velocity varies according to mass, size, and shape of a falling object. And so you have a kind of a picture there on the side of velocity. You have a falling object accelerates at a constant rate. Each second, the object travels faster and farther than it did the second before. So you can see the distance between the tennis balls. You have the first second, the ball moves 4.9 meters. The second, it moves 14.7 meters. And the third second, it moves 24.5 meters. So it is increasing in distance and in speed. Terminal velocity, the force of air resistance pushing up, and the force of gravity pulling down. Until the ball reaches terminal velocity, net force keeps it accelerating downward, but not as fast as it would without air resistance. A skydiver wears a parachute to reduce his or her terminal velocity. The parachute does not change the diver's mass, but increases the surface area, so more air can resist the fall than decrease the terminal velocity. Because the acceleration of gravity is constant, the distance an object travels in free fall can be calculated if the time it falls is known. The equation d equals half times a times t to the second shows the relationship between acceleration, the distance traveled, the time that something falls. In this equation, d is the distance traveled, t is the time, and a is the acceleration. If you drop an object and measure the time of the fall from the moment you let the object go until it hit the floor, you can calculate the distance of the fall. What distance did an object fall if it took 0.75 seconds to reach the ground? So your formula would be d equals half times 9.8 meters per second times 0.75 seconds squared equals 2.75 meters. The acceleration of gravity also affects the motion of projectiles in a predictable manner. Projectile motion is the curved path an object follows when thrown or propelled near the Earth's surface. The motions of leaping dancers, thrown balls, hopping frogs, and arrows shot from a bow are examples of projectile motion. Projectile motion has two components, horizontal and vertical. The two components are independent, that is, they have no effect on each other. When the two motions are combined, they form a curved path. Think about a shooting arrow. The bow's force on the arrow makes the arrow move forward. The force results in horizontal motion. After the arrow is released, no horizontal forces except air resistance are acting on the arrow, so the horizontal velocity of the arrow is constant. After the arrow is released, gravity pulls it downward, giving it vertical motion. Projectiles accelerate downward with the acceleration of 9.8 meters per second, as do all falling objects. Because objects in projectile motion accelerate downward, the archer must aim above the target instead of directly at it. And there you have kind of a description with a slingshot there. So after the projectile is launched, its horizontal velocity is constant. The horizontal velocity and vertical velocity combine to form a curved path. The projectile's vertical velocity increases as gravity causes it to accelerate downward. So if you're pulling back and you let go a stone from a slingshot, it's going to move forward If there was no gravitational pull, it would keep going at that horizontal plane forever. But because there is gravitational pull at the same time, it's not just going out and straight down, because you have a balance between the horizontal velocity and the gravitational pull pulling it down, the vertical velocity. And so those two things combined, you end up with a gradual curve of the object hitting the ground. So if you shoot an arrow, if you want to shoot close range, you would shoot pretty straight. If you wanted to shoot long distance, you would aim farther up to account for that curve of going up and then back down. That's why things like archery take skill and practice, because you need to know at what angle should you be shooting in order for it to land on your target. Okay, so some questions to answer today based on what we read. What is the law of inertia? When a ball rolls across the floor, why does it stop moving? Imagine that two objects of differing mass have the same acceleration. Which is the greater force acting on it, and why? If a man pushes an object with 210 newtons of force and an object resists with 150 newtons of force, what is the net force? If the object accelerates at 2 meters per second, what is the object's mass? If the acceleration of gravity is constant, why is terminal velocity different for different objects? If a planter is knocked off a ledge and falls, if a planter is knocked off a ledge and falls at 1.2 seconds, how far does it fall? What two components create the curved path of projectile motion? There are a couple try lists, so if you want to give those a try, you can go back and read those. For your lab for today, if you have the materials to do this, give it a try. For acceleration of gravity, the question being posed is, do all objects fall with the same acceleration? And materials you would need in order to complete this lab today are a table tennis ball, which is a ping pong ball, a small rubber ball, a meter stick, and 5 basket type coffee filters. So the white coffee filters you would put in the basket of a coffee pot. So if you have those things, give this lab a try. I know you guys meet for reading at the church, so you might find the materials there at the school, and I know there's a meter stick, so you can give that a try. For another lab, if you have the materials for it, projectile lab in motion, which is lab B. When launching a soft dart, what is the best angle for the greatest distance? So things you would need for this are a soft gun dart, like a Nerf gun that shoots the darts, soft darts, a large protractor, a meter stick, and masking tape. So if you have access to Nerf guns, that have darts, you can give this a try as well and graph what that curve looks like. If you have any questions, please let me know, and I will see you next time when we go on to 9.14, which is circular motion.